AI capability has reliably followed three distinct scaling curves: expanding the volume of pre-training data, refining post-training optimization, and, most recently, increasing test time compute. Because of this investment, current models map out highly complex actions in real-world environments, branching through dozens of decisions to reach a final goal. But generating these sprawling decision trees exposes a structural flaw. The speed at which models produce complex sequences has outpaced our capacity to verify if those individual steps are actually correct. A single agentic task often requires hundreds of micro-decisions. Tracking and validating this volume of outputs using human-in-the-loop evaluation is physically impossible at scale. We have scaled how these systems generate, but we have ignored how they evaluate. The absence of a dedicated scaling axis for verification is the single primary barrier to reliable, fully autonomous AI deployment. The current industry standard for evaluation relies on prompting a language model as a judge. It reads an output and assigns it a single discrete integer, usually between 1 and 10 or 1 and 20. Forcing the model to select a single integer obscures its internal probability distribution. The nuanced uncertainty metrics are discarded to produce a single, rigid response. In practice, this causes operational gridlock. When comparing two highly complex codebases containing only slight flaws, it frequently assigns them the exact same integer score, resulting in unresolvable tie rates. Researchers from Stanford and Berkeley developed the LLM-as-a-Verifier framework to bypass this constraint. Instead of relying on the text output, this system calculates the expected value across the model's entire scoring token logit distribution. Accessing raw log probabilities converts the model into a source of continuous, high-resolution feedback. Under this framework, we completely ignore the final text generated by the model. The data we need exists exclusively in the log probabilities of the specific tokens the model considered before generating its response. Extracting this data requires a precise adjustment to the prompt. The framework strictly prohibits asking the model to evaluate using numerical digits. The math fails with numerical scoring because digits frequently tokenize inconsistently, depending on the architecture of the underlying language model. The system mandates a letter-based scale, like A, B, C, or D. A single alphabetical letter extracts cleanly across architectures, mapping perfectly into a usable probability vector. By calculating the expected value across this specific array of log probabilities, the system computes a continuous, floating-point score that captures the model's precise confidence level. This simple prompt-level adjustment successfully converts a standard zero-shot language model into a continuous reward signal without a single gradient update. This outlines the LLM-as-a-Verifier architecture, relying on four mechanisms. The foundation is this expectation equation at the bottom, mapping discrete letter-based inputs into continuous probabilistic distributions. Let's examine the first test time scaling axes in the top left quadrant: granularity. By extracting a wider array of scoring token logits during evaluation, the model constructs a higher resolution view of the problem space. This high-resolution continuous score heavily pulls edge case positive and negative trajectories apart, directly solving the tie rate problem caused by discrete integer judges. Scaling granularity provides the mathematical separation required for an autonomous agent to accurately identify its own incremental progress. Moving to the top right quadrant, we find the second scaling axis: repetition. A single evaluation pass carries inherent noise, so we repeatedly sample the score, aggregating outputs to reduce variance. The final axis, decomposition, shifts focus to cognitive load. When an LLM judge is fed an overwhelmingly complex monolithic task, it frequently exhibits prompt bias, artificially skewing its confidence distribution. Decomposing complex criteria into modular, independently verifiable microsteps tightens the confidence bounds of the extracted logits. Scaling granularity, repetition, and decomposition simultaneously yields a highly predictable, computationally scalable verification engine. The current MLOps standard for evaluating trajectories relies heavily on training bespoke process reward models and outcome reward models, a pipeline that is both data-hungry and expensive. These explicitly fine-tuned models are brittle, often failing when pushed out of their specific training distributions. The LLM-as-a-Verifier framework operates completely zero-shot, allowing it to generalize across entirely new domains. The data confirms the advantage. the framework achieves state-of-the-art verification accuracy across distinct, highly complex disciplines: SWE Bench for software engineering, MedAgent Bench for medical tasks, and Robo-Reward Bench for robotics. Because this continuous signal operates at such high fidelity, it enables the evaluation of complete chronological interaction trajectories, rather than limiting judges to isolated intermediate steps or static final outcomes. Applying scaled compute during inference has proven more effective for generalized verification than relying on specialized, data-intensive fine-tuning. This verification framework also functions as a tool for active model training. Current reinforcement learning algorithms like SAC and GRPO struggle with sample inefficiency. They rely on sparse binary reward signals, a simple pass or fail generated at the very end of a long task. Injecting the continuous logic distribution directly into the reinforcement learning process replaces that sparse binary with a dense, high-frequency learning signal. On robotics benchmarks, this dense signal achieves 1.8 times higher sample efficiency than sparse reward baselines, while also reaching a higher final success rate. Verification is no longer a passive bottleneck. By converting test time compute into dense continuous rewards, it serves as a primary mechanism for improving model performance during training.